So yesterday we had ended at this page. So what was this again? So we are studying rectangular waveguide. So we required to find the electric field and magnetic fields in each and every direction, that is x, y, z. So we had found out Ez. How we had found out this Ez? Do you remember? We had found out using wave equation. We used del square Ez equal to minus omega square mu epsilon Ez. Then we applied method of separation of variables. Then we had 6 constant. Iteratively using boundary conditions, we solved all the constants, found their value, and finally we were left only with 3 constants, which we assumed as a single constant C. Then we said that we are not interested in finding the amplitude as we did in antennas, because it is just a number. So we are interested in the actual equation, what is happening, right? So this is how we arrived at Ez. And since it was a TM mode, what was happening? Magnetic field was transversed to the direction of propagation, and there was no field in the direction of propagation. Since there was no field in the direction of propagation for that is magnetic field, so Hz was 0, right? So for TM mode, Hz is always 0. Similarly for TE mode, Ez is always 0, right? So we found out this. Then we said analysis of waveguide in general, using general approach topic we have, which is not in the syllabus. From that we get the values of Ex, Ey, Hx and Hy. So we substituted those formulas and substituted the values of Ez and Hz there. So finally we got Ex, Ey, Hx, Hy. So in this way we got Ex, Ey, Ez, Hx, Hy, Hz, right? So these are all the equations, okay? And don't forget, we also had the value of H square, which is omega square mu epsilon minus beta square equal to m pi by a the whole square plus n pi by b the whole square, right? So let's see what is the meaning of this. So if you remember in parallel waveguide, parallel plane waveguide, sorry, we had only one constant, that is m. But what is happening here? We have m. Apart from m, we are also having n. So we have mn. So if you see TM mode of a parallel plane waveguide, what were the modes? TM0 was not existing, but TM1, TM2, etc. further apart were existing. That is, the modes were TMM, I can say, where m indicates the, and I can say m is not equal to 0. So in the same way, I have, instead of m, I have mn. So these modes are called as what? TMMN modes. Okay, so these are called as TMMN modes, remember. Okay, so this is the first thing we understood. So next, let's note down the points what we learn from these equations. Again, as I always tell right from the electromagnetics course, don't see them as mathematical equations, see them as concepts. Then only you will be able to comprehend them, and then only the equations will be beautiful. Okay, so what is the first thing we see? The fields again are existing in discrete patterns. Why we say discrete patterns? Because if m and n changes, we will get different patterns, right? So we have seen that in parallel plane waveguide. Depending on m value, we have different patterns. That is, we have 1 half cycle variation, 2 half cycle variations, and so on. So we say field exists in discrete patterns called modes of the waveguide, right? Second, what we say? So if you observe, all the components are having sinusoidal variation. Now you might say, sir, there is cosinusoidal variation, but we can say it is nothing but transferred by or with a space of 90 degree, right? So even if it is sine or cos, we say it is sinusoidal only. So second, we say all field components have sinusoidal amplitude variation, in x and y directions. Okay, next point, what we see? So we have, instead of one subscript, that is m, we have 2 subscripts, m and n, right? So subscripts. So why am I calling them subscripts? Because the mode is designated as what? TMMN mode. So these are subscripts m and n. So subscripts m and n represent number of half sinusoidal or number of half cycles, you can say it is assumed it is sinusoidal, half sinusoidal cycle in x and y direction. Why we say only x and y? Because here you take x and y, right? You see x and y here. That is the reason. So next, let's substitute the value of m and n as 0, starting from 0 as we did in the parallel plane waveguide case. Okay. So what is happening? So let's say first m is 0. So what will happen? Ez will go to 0. Hz is already 0. What m is 0, right? So this will not go to 0. So ex exists. So I'll put a small tick mark there. These are going to 0, so I am not putting a tick mark. So if m is 0 again, yeah, so this exists. So ey, what is happening to ey? Ey is going to 0. So only ex is there. Hx is also going to 0. And this m, we have a constant term here. So hy is also going to 0. So we have only electric field. Right? Have I made a mistake? Let me check Ex equation. Yeah, I have made a mistake. I have missed m pi by a. It is multiplied by m pi by a. So this will also go to 0. So what is happening when m is 0? All the terms go to 0. Means no electric field, neither electric field nor a magnetic field exists. Right? So what does this indicate? Tm0n. We have not substituted n, remember. So this indicates Tm0n. Whatever be the value of n, if n is 0, this mode will not exist in the rectangular waveguide. So that is what is our conclusion. Again, we are trying to understand the meaning of equations. Then only they will become beautiful. So slowly and gradually, we are understanding the equations now. So let's substitute n equal to 0. Right? So when n is 0, again this goes to 0. This is 0 already. So n is 0, so ex also goes to 0. When they are existing, I am putting a tick mark. So n is 0. So ey here again I have missed, it is multiplied by n pi by b. Okay. So this is ey. So ey also goes to 0. This is hx. Hx also we have n pi by b. Okay. So again this also goes to 0 because we are taking n equal to 0, and this also goes to 0. Means what? Whatever be the value of m, Tm, whatever be the value of m, m0, that is when n is 0, this cannot exist. Right? So can I say together, what can I say? I can say that in fact combining these two, Tm00 cannot exist. Then I can say Tm01 cannot exist. Tm02 cannot exist. Further, Tm10 cannot exist. Tm20 cannot exist. Right? So what is the lowest order mode that can have? Means m cannot be 0, n cannot be 0. So m next lowest number is 1. So m and n should be 1. So m equal to 1, n equal to 1. So we substitute m and n as 1. So m is 1, n is 1. So this equation exists. So this is already 0. So again this equation exists, this exists, this exists, this exists. Right? Means the fields exist for m equal to 1, n equal to 1. So what is our conclusion? Lowest order mode is what? Tm11. So I can say Tm11 is the dominant mode in a rectangular waveguide. When we are considering Tm mode, remember. So it is the dominant mode when, no, I made a mistake. So we'll discuss about dominant mode later when we are done with T mode also. Okay. So that at that point we'll see what is the dominant mode here. So we say all transverse fields go to 0 if either m or n is 0. Right? Means what? We can say that is Tm0n and Tm m0 modes cannot exist, right? So what we can conclude? So therefore, lowest order mode in rectangular waveguide. What is it? It will be TM11, right? So this is the lowest order mode. So these are the four conclusions which we derive. Fine. So this is about what TM mode. So similarly, we'll see for what transverse electric, that is TE mode, right? So what is our conclusion again from TM mode? That TM0N and TMM0 modes cannot exist. So the lowest order mode is TM11, right? And this type of mode is called as in general TMMN. Why it is TMMN? Because we have two indices M and N. In parallel plane waveguide, we had only one index. Okay. So let's see TE mode. Right. So again, it is TE mode, means transverse electric mode. Means electric field is only the electric field component is transverse to the direction of propagation. Means what? It does not have any direction in the any propagation in the direction of Z. Right. So I can say Ez is 0 and Hz is not 0. Right. So it was the other way around in TM mode. So if you see, we got Hz as 0 and Ez some value. So here we should get Hz some value. So again we'll use wave equation. So del square Hz equal to minus omega square mu epsilon Hz. So I will not solve it. You can solve it. This will be self-study. Not in fact self-study. I have taught the first part. So now this is for TE mode. You can do it yourself. So what we will do, daba square is daba square by daba x square plus daba square by daba y square plus daba square by daba z square. Then take this here. So we'll get one equation equal to 0. Then we will use separation of variables. So we'll say hz is a function of x, y, z. Again, then we'll solve this. Then we will have C1, C2 till C6. So we'll find these values and finally we'll get Hz. Right? So this is the way you will solve. So I'll directly write the Hz value. So first we have got Ez is 0. So next is Hz. So Hz if you solve, you will get it as D. I am taking D because the reference book has taken D. If you want, you can take C also. Why they have not taken C is because it is already assumed for TM mode. So cos of m pi x by A into cos of n pi y by B e raised to minus j beta z. Then similarly, then we'll use those previous equations using general approach. So we'll get what? Ex, not Ez. So Ex will be j omega mu by h square into D into n pi by B into cos of m pi x by A sin of n pi y by B e raised to minus j beta z. Then we'll have Ey. It will be minus j omega mu by h square m pi by A into D sin of m pi x by A cos of n pi y by B again into e raised to minus j beta z. I hope everyone remembers what does this e raised to minus j beta z term means. What does it mean? It means that wave is traveling in plus z direction. So if this is minus, it indicates positive z. So we have seen this in basic electromagnetics course. So equal to j beta by h square m pi by A into D sin of m pi x by A cos of n pi y by B e raised to minus j beta z. Then finally we have hy. So what is hy? J beta by h square n pi by B D cos of m pi x by a sin of n pi y by b e raised to minus j beta z. Again, if you solve h square, sorry, it will be m square m pi by a the whole square plus n pi by b the whole square, which is omega square mu epsilon minus beta square. So h square value is same as tm mode, right? So let's see what do these terms mean, right? So this is which mode? Rectangular waveguide TE mode, right? So again, the first three conclusions will be same as the previous thing. Okay, so what are those conclusions? That page. So first we observe again fields exist in discrete patterns. Why they exist in discrete patterns? Because it depends on value of m and n. So fields exist in discrete patterns called modes of the wavegate. Then now again we see all the field components have sinusoidal variation. So all field components have sinusoidal amplitude variation in x and y direction. Right? Then what we see? Again subscripts m and n we have, this is m, this is n. So subscripts m and n represent number of sinusoidal cycles in x and y direction. So first 3 points are same. Only the fourth point will. So let's see what it means. So these are all the equations: ex, ey, ez, hx, hy, z. So ez is 0. Then we have z, ex, ey, hx, hy. So we have all the equations, right? And again, so this is TE mode. So m and both exist. So what is this mode called as? TE-MN mode, right? So this is designated as TE-MN mode. So let's see which is the lowest order mode. So first what will be substitute? Again m equal to 0. So this is already 0. So if m equal to 0, this goes to 1. So this exists, right? So let's put a tick mark here. So m is 0. So m is 0. So this also exists. So m is 0. Yeah, this exists. So m is 0, this goes away, this goes away. Then this exists, right? So means we have ex and hy both terms and both are transverse. So ex will be like this, hy will be like this. Means what? When m equal to 0, the mode is existing, right? But you have to see together n also. So let's say if m is 0 and n is 0. So n is 0, so this exists. So this is still existing, right? So let me use a different pen. So this exists. So n is 0. So this does not exist for n is 0, right? So n is 0. So this exists. So n is 0. This exists. So n is 0. This does not exist, right? So we are having for m equal to 0 some fields exist. For n equal to 0 some fields exist, right? So what is happening when m is 0 and when n is 0? What is existing? Only hz exists, right? But only magnetic field cannot exist. We need to have a corresponding electric field also. So since Ez is already 0, hz also cannot exist. Means what? M equal to 0, n equal to 0 cannot be the case, right? So TE00 mode cannot exist. So that is our conclusion, right? So next, let's say m equal to 1. So what is happening for m equal to 1? This does not exist. So I'll use the right side. So m equal to 1, this is already not there. So m equal to 1. So this exists. Yes. So I think all will exist now. So this exists, this exists, this exists, this exists. Right? Because m is 1. Now n is 0 will put. Let's see what happens with n is 0. So n is 0, this is obviously not there. So n is 0. So again this exists. Right? Yeah. So n is 0, this does not exist. N is 0, this exists. So now Ey exists. So n is 0. So again this exists. So we have Ey hx perpendicular components. Means this mode exists, so we don't have to see this. So what we had put, I forgot. We had put m is 1 and n is 0. Right? So TE10 exists. So let's next put TE01. So if you observe, this will also exist. Means what does it indicate? Either m or n has to be non-zero. Okay. So this indicates that m or n has to be non-zero. That is our conclusion, right? So let me write that here. So 1 is same, 2 is same, 3 is same. So fourth is either M or N has to be non-zero for some of the fields to exist. Why we say some? Because both M and N cannot be zero. Then the field won't exist, right? Then we say, I'm not writing in detail, you can refer in the notes that I upload. T00 mode does not exist. Why it does not exist? Because all the fields vanish. Yes, Hz exists for both values of M and 0, but since Ez is 0, Hz also cannot exist, because we have seen there is interdependence of electric and magnetic field from Maxwell's equations. Right? So what are the lowest order modes? They are, so the modes can be TM0 and TE0N exist. So lowest order modes. So this can be Viva questions. Lowest order modes are TE10 and TE01. So these are the lowest order modes. Okay. So this can be Viva questions, right? So next, what is the last mode we see? TEM mode. So let's see whether this exists or no, right? So we had seen in a parallel plane waveguide, TM0 mode is nothing but the TM mode. That is, both the modes are same. So if you don't know this, let's just see the parallel plane waveguide series. There were 3 parts, I suppose. I think it is a part 3. I think it is in part 3. I'm not sure. So you just see that, right? So let's see whether TM mode exists in a rectangular waveguide or no. It exists in a parallel plane waveguide, right? So let's assume that the TM mode exists in a rectangular waveguide. So we can prove it mathematically, but let's do it conceptually because it is simpler, right? So how was our axis given? So this was our rectangular waveguide, right? And how are the axis oriented? This was my Z axis. So Z, this was my Y, this was my X. So this is X, this is Y. Right-handed coordinate system. If thumb points in the direction of Z, X to Y gives me what? Direction from X to Y. Right? So let's say the mode exists. So if the TM mode exists, we know it is transverse electromagnetic mode. Right? Means what? Electric field is in which direction? We say it is along the X direction, and magnetic field is along Y direction, right? So if you remember that reflection and reflection lecture, or in parallel in parallel plane waveguide first part. So this was our Z axis, this was our what? X axis, this was Y axis, right? There is no need of taking this analogy. What we can do, electric field and magnetic field will be transverse to the XY plane. Sorry, they will be in the XY plane only because it is transverse electromagnetic mode. Transverse indicates perpendicular to Z, perpendicular to the direction of propagation. So XY plane will have electric and magnetic fields. So let's arbitrarily assume E vector is along X direction and H vector is along Z direction. Okay. Now what we know, magnetic field, if you have to draw it completely, it always forms loops, closed loops, right? How do we know that? We know Ampere's law. If current is flowing in the upward direction, by Ampere's law, direction of magnetic field is given by right hand rule. So for this case, it will be like this. So it always forms closed loops. So this will also form a closed loop, right? So let's say it forms a closed loop like this in the xy plane, right? So since this is going upwards, this has to be upwards, here it will be downwards, right? So what we have said, magnetic closed loop will be there. So what we are saying again, TEM mode, we are assuming it is existing. So since it is TEM mode, x and y will be corresponding to E and H vector, right? So then we say magnetic fields always close on themselves. So magnetic field is like this. So this is my H vector. So this is Ampere's law. So if magnetic field exists, obviously a current should be flowing inside. Means, so again this is in xy plane. So by converse of Ampere's law, a current should flow, right? So this is going like this. So current should come towards the camera or towards the viewer. So current should come like this. But if current should come, there should be something, some current carrying medium here. That is a good conductor should be there. But there is no good conductor. Means this current cannot flow. If this current cannot flow, then magnetic field lines cannot close on themselves. So if magnetic field lines cannot close, means H vector does not exist. If H vector does not exist, by Maxwell's equations, E vector cannot exist. That is, our assumption is wrong. Means TEM mode does not exist in a rectangular waveguide. Understood? So this is our conclusion, right? So again, if you have not understood, just rewind the video and see. So finally we have cutoff frequency for rectangular waveguide. So what we know, h square is omega square mu epsilon minus beta square equal to m pi by a the whole square plus n pi by b the whole square. So what will be beta square from this? So beta square will be omega square mu epsilon minus of m pi by a the whole square. This is minus n pi by b the whole square, right? So what will be beta? Square root of omega square mu epsilon minus m pi by a the whole square minus n pi by b the whole square, right? Then we have to find cutoff frequency. Again, what is cutoff frequency? The minimum frequency at which the propagation in the waveguide starts. Means waveguide cannot propagate or all frequencies. So electromagnetic wave, all frequencies of electromagnetic waves cannot propagate except TM mode, because TM mode is non-dispersive. Why it cannot propagate? Because of the concept of dispersion, right? So if you solve this 2 pi by lambda, then lambda is v by f and all, or in simple words, beta should be real. So this value should be greater. So then you solve this. So omega is 2 pi by f. So you will get omega c is 2 pi f, sorry, omega c equal to 1 upon square root of mu epsilon square root of m pi by a the whole square plus n pi by b the whole square. Okay, so this is what cutoff frequency, right? So what will be fc? fc will be 1 upon 2 pi root mu epsilon square root of m pi by a the whole square plus n pi by b the whole square. So this is what cutoff frequency, right? So what is the, so we want to find the dominant mode now. So dominant mode is taken considering both the modes TE, TM and TM modes. So that's why I stopped from telling you the dominant mode last in some a while ago. So for TM it is TM00, sorry, TM11, right? So what will be FC? TM11. So this will be 1, this will be 1. So what will you get? 1 upon 2 pi square root of mu epsilon square root of pi by a the whole square plus pi by b the whole square, right? Similarly for TE10, lowest order modes are TE10 and TE11, right? So for TE11, sorry, TE10 you will get 1 upon 2 pi square root of mu epsilon 10. So m pi by a the whole square, m is 1. So FC TE10, after solving, pi will get cancelled. So it will be pi, sorry, 1 upon 2a root mu epsilon. Similarly, you calculate for TE01. So you'll get FC TE01 equal to 1 upon 2b square root of mu epsilon. So we want to find, these are the lowest order modes. TM mode does not exist, so that is not a question. So this is the equation, this is the equation, and this is the equation, right? So you want to find the dominant mode. Which among these should be the dominant mode? The one with the lowest cutoff frequency, right? That is how we have defined dominant mode, right? So let's see what is happening, right? So lowest cutoff frequency will be where? So if you see, this is my A. So A is higher because we have defined A as broader dimension. So A is always greater than B, right? So if you substitute for TM11, it is what? Under square, right? So here you have both terms A and B, but here you have only A, here you have only B. So since you have both A and B, obviously this will be higher, right? Because the terms are getting added. That is the reason this will be higher. So TM11 is the, among this, has the highest cutoff frequency, right? Now this is the question, it is the question of T10 and T01. So we know A is greater than B. So since A is greater, this frequency will be lower than this frequency. That is what I mean to say is FCTE10 is less than FCTE01, and which is less than FCTM11. So this is our what we have derived. So what does it mean? That TE10 mode is the dominant mode in a rectangular waveguide. Okay, so this is what we learn from rectangular waveguides. Okay, so similarly you can write the equation for lambda c. You know FC, so you can write lambda c, right? So this is what we learn in this lecture. Okay, so next time we'll do numericals on this. Thank you.